Hi, we will discuss time domain specifications. Consider a system whose closed loop transfer function is given as C of S by R of S equal to omega n square by s square plus 2 zeta omega ns plus omega n square. This is the standard transfer function where omega n is the natural frequency of the system and zeta is damping coefficient. If zeta equal to 0, we call the system as undamped system. If zeta is between 0 and 1, we call the system as underdamped system. If zeta equal to 1, we call the system as critically damped system. If zeta is greater than 1, we call the system as overdamped system. If input is step input, then your R of S is equal to 1 by S. So from the previous slide, from this transfer function, C of S can be written as R of S, that is 1 by S, into omega n square by S square plus 2 zeta omega ns plus omega n square. Okay, so then how to calculate the C of t? C of t is nothing but L inverse of C of S. Okay. So for different values of zeta, we can find output C of t. If zeta equal to 0, then C of S is equal to 1 by S into omega n square by S square plus 2 zeta omega ns. That term will become 0 because zeta is 0. So omega n square. So to get C of t is nothing but L inverse of C of S. So after doing partial fractions, what output you will get is, first we will plot the input and output. This is time axis and this is amplitude. So this is the step input, unit step input. Okay. Then your output is like this. Output C of t is nothing but 1 minus cos omega nt. Okay. The frequency here is omega n. Okay. So output is sinusoidal function. It is oscillating. So for undamped system, that is for zeta equal to 0, if you apply step input, then the output is oscillatory. Okay. Now second case, underdamped case. If zeta is between 0 and 1, then your output C of S is 1 by s into omega n square by s square plus 2 zeta omega ns plus omega n square. So C of t can be calculated by taking inverse Laplace transform of C of s. So that is nothing but 1 minus e power minus zeta omega n t by square root of 1 minus zeta square into sine omega dt plus phi. So here omega d is nothing but omega n into 1 minus zeta square, and phi is tan inverse of square root of 1 minus zeta square by zeta. Okay, so here this omega d is damped frequency, omega n is natural frequency. So if I plot both input and output here, so this is the unit step input that I have applied. Now the output is it will be something like this. So this is output C of t, output C of t. So for underdamped system, that is for zeta between 0 and 1, if we apply step input, then the output is oscillatory, not pure oscillations, just it will rise above the input, it will reach the peak amplitude, after that it will decay, and again it will increase and decrease, and finally after some time it will settle down, it will reach the steady state. This is for underdamped system. If zeta equal to 1, then directly I plot the input and output. If this is the step input, this is input, step input, then the output is simply exponentially rising characteristic. This is the output. If zeta is greater than 1, that is overdamped case, then the output is similar to critically damped case, but with higher riser time, with high rise time. Say I can plot here itself. This is the case. So this is for overdamped case. In overdamped case also, the output is exponentially rising like critically damped system, but with higher rise time. Okay. Thank you.